Good morning, guys. So we'll be starting with the rest of the portion, and I hope you remember we stopped with the topic which is apparent dip angle, and we found a relationship between apparent dip angle and true dip angle. So there are two types of dip angles. One is apparent and the other is real. Real dip angle is an angle which is made by the dip needle with the horizontal of a magnetic meridian, whereas apparent dip angle is angle made with the by the magnetic needle with the horizontal of another plane which is other than magnetic meridian. Right? This and all I have taken in the previous class. If you have not understood or if you have not gone through the previous video, there is no meaning if you are listening to this video. So I request you guys to go back if you have not learned till now the portion which has been taught in the previous week. That is, I think that is on Thursday I have put the video, half an hour video. Please go through it. Until and unless you are sure about it, don't go for this video. And today we'll be having 1 hour live class also. So again, I hope you have listening to this video, then after this video only you are listening the live class, because live class will be the continuation of half an hour video which is uploaded on the same day. Okay guys, so shall we move on? Okay, we found this relation. I hope you by heart this relation. Now related to this topic, I'm going to do a small problem so that this consideration of this topic will be very thorough for you guys. Okay, now let's move on to the numerical question. Okay, now the question is, if a magnetic needle as also a magnet, if a magnet is suspended at an angle 30 degrees to the magnetic meridian, so this is actually a magnetic needle. I hope you understood that. So there is a magnetic needle which is suspended at an angle 30 degrees to the magnetic meridian. So there is a magnetic meridian like this, right? And meridian, okay, and the dip needle makes an angle 45 degrees with the horizontal. I hope you understand the question. See guys, there is a magnetic needle. That needle is not lying on the magnetic meridian, because if it had been lying on magnetic meridian, you will not say that the needle is making 30 degrees to the magnetic meridian. They would have told horizontal or vertical, etc. You have told that the magnetic needle is suspended at an angle 30 degrees to the magnetic meridian, means there is a needle which is lying in another plane other than our magnetic meridian. Right? Clear? This is the needle, say, and this needle is making 30 degrees with the magnetic meridian. This is your magnetic meridian, right? This needle is making 30 degrees with the magnetic meridian. So that means I can say actually 30 degrees the angle between this. Where is this needle lying? This needle is lying in another plane, because it has been told that the magnetic needle is making an angle 30 degrees on the magnetic meridian. So it is not lying on magnetic meridian. So it is lying in some other meridian or some other plane. Say this is the plane 1. So it is lying in plane 1. So if it is lying on the plane 1, so the angle made by the needle on the magnetic meridian is same as that of angle made by this plane 1 with magnetic meridian. I hope this much is clear. Right, so I can say this 30 degree as per our previous case is theta. That is the angle between the planes, that is magnetic meridian, the plane which is in the question. So theta is 30 degree. This much clear. Now there is another angle mentioned in the question. The dip needle makes 45 degrees with the horizontal. So which horizontal? This horizontal. So this is your 45 degree, or what is this angle called? That is known as apparent dip, that is delta dash is equal to 45 degree. This is given. Now you are asked what is the true dip or real dip. That means you are asked delta. So tan delta dash is equal to tan delta divided by cos theta, right? The previous equation. In tan delta dash I am writing tan 45 degree, which is 1. I hope you remember. Tan delta, this is to be found, divided by cos 30 degree. What is cos 30 degree? Root 3 by 2. So it goes over here. So root 3 by 2 is equal to tan theta, or it's not theta, delta. That means delta is equal to tan inverse root 3 by 2. That is the answer. Clear? Now we are moving on to the next major topic. Again guys, today is a theory topic session and I hope we will be doing numerical section in the live class. I'll try to do it. Now I'm not, while taking the live class, we'll take a few bits. You can see me, I can see you guys, and then I will reverse the mobile and we'll try it the same way only. I will be taking the live class also, because screen sharing etc. when I saw and when I tried, when I'm writing on the mobile's whiteboard, it doesn't look good, right? So our end result, what we require is you understand the topic. That's what we are going to do, right? So the first topic or the theory topic today we are going to deal is cause of magnetism in matter. We have dealt with cause of magnetism in the case of an atom. I hope you remember how in an atom the electron is revolving around the nucleus. The revolving electron causes current. Current is just like a coil carrying current. That means there is an induced magnetism. So there is a magnetism and there is a magnetic moment, and that magnetic moment M is equal to IOA. This much portion I have taken in the previous section itself. So I'm continuing from that topic. Now, in some elements like say helium, this is chemistry which you have learned, right? The magnetic moments are cancelling out each other. I'm telling you how. See, you would have written this type of method, right? That is, you will write right, helium is having 2 electrons, 1 s2, right? The 2 electrons, you will write it like this. So that means they will say this termed as paired electrons. Remember? They are paired electrons, right? So in these type of things, these electrons are cancelling out each other. What is being cancelling out? See, this is the magnetic moment of the first electron and this is the magnetic moment of the second electron, and they are cancelling each other. Hence, the net magnetic moment of helium is 0. So this type of materials or matter which are having paired electrons will have what? 0 dipole moment or 0 magnetic moment, and this type of materials are called, I hope you remember, diamagnetic materials. They are diamagnetic materials. Their net dipole moment is equal to 0. This is what happens in the case of a diamagnetic material. The example is helium. NaCl etc. are also diamagnetic material. Water is a diamagnetic material. Anyways, let's move on. Now, whereas there are some other elements, so then you have to understand how did I draw dipole moments etc. That I am going to take how it came up, okay? I hope you remember the electron motion which I just told you in the case of a single atom, right? So each element or each matter you consider, each matter is a clump of lot of atoms, so there will be a clump of electrons. So each electrons, when I consider, each electron is causing what? Each electron will be causing current, each current will cause what? A magnetic moment, right? So in that way there is a collection of magnetic moments. In the case of diamagnetic materials where there are pair of electrons, one magnetic moment is in this direction. If it is spinning due to the current electron spinning, if the moment is in this direction, there will be another electron, the paired electron will be having the magnetic moment in opposite direction, so that they cancel it out, right? So I can say every material you can term as a collection of atomic dipoles. What it is? Collection of atomic dipoles, right? So there will be magnetic moment in what? Only in paramagnetic and ferromagnetic objects. No magnetism or no atomic dipole you can see in the case of a diamagnetic material. This much clear? Now we are going to consider para and ferromagnetic material in detail. Right. In para or ferro, that the atomic dipoles are randomly aligned. That is, suppose I consider this is either a ferro or a para, guys. No, I am not explicitly telling this is para and this is dia. So this is a model. Then we should there is lots of electrons, lots of atoms, or now each atom will be having its own distinctive dipole moment. And these atoms are randomly arranged. Dipole moments are like this, right? So no net dipole moment will be there, right? Why? Suppose I consider small area like this. Okay, I have to draw the picture a little bit larger so that suppose there is a dipole moment here, then another dipole moment like this. Directions, okay. So when I consider a unit volume like this, right, or like this, let's say like this, I consider unit volume. I'm having one dipole moment in this direction, another dipole moment in this direction, right? I'm darkening it, guys, so that you will understand. This is the area I'm going to consider unit volume. One dipole moment is in this direction, another dipole moment is in this direction, so that the dipole moments are cancelling out. So the net magnetic moment in the ideal case, as it is when the ferro or paramagnetic, when it is kept without any energy source or just kept as it is, the net magnetic moment is 0. Now what I'm going to do is, in this scenario, I'm going to apply an external magnetic field. So the same figure, right, now I'm going to apply an external magnetic field B. Right, now this external magnetic field, what it does, so it is seeing many large amount of atoms which are having its own dipole moment, right? So I can say dipole, right? I hope you remember electrostatics also, you learned electrons, remember, plus Q minus Q, when they are kept in external field, what would they do? They rotate, or remember, they produce a torque. Similarly here, each electron, right, it is spinning, it is acting as a current carrying coil. Remember, current carrying coil in an external field will experience a torque, right? Similarly, this torque, right, will be experienced by each dipole inside this ferro or paramagnetic material due to the application of external field. This torque will align these dipole in a direction, right, in a direction as that of the applied magnetic field, right? So suppose initially it was in random, now all the dipoles will be not exactly straight but similar in this direction, right? Now so that now the net magnetic field is not equal to 0. Initially the net magnetic field without application of magnetic field, external magnetic field, as it is when the paramagnetic or ferromagnetic material was kept as it is, the net magnetic field was 0. Now when I applied an external magnetic field, it exerted a force, I would say exerted a torque on the dipole inside the material, and they aligned in the same direction as of the applied field, so that the net magnetic field is now not equal to 0. This is a case of, again guys, para and ferro. Diamagnetic case, there is no net dipole moment inside it initially itself. So application of magnetic field will be having a different characteristic, which I will tell you later on what happens. Right, now let's deal about only ferro and para. Right, now the alignment, this alignment can be made proper. I told you when you apply magnetic field, they will align due to the torque application, but not in a straight way, right? If you want to align them in a particular direction itself, you can either increase the applied magnetic field or you can increase the temperature. By both of them, you can increase the alignment. Now, another question is, what will be the, suppose the induced magnetic field? Now, see, these dipoles are arranging themselves, right? Arranging themselves in a direction, so they will be having their own magnetic field inside. Let's say that is inside, right? BI. That is inside magnetic field will be there. What will be the nature of inside magnetic field and outside magnetic field? Which is greater? Okay, my pen stopped. Which is greater, guys? Inside magnetic field is greater than outside magnetic field. Why? See, external field is having only one job. It is just aligning it, right? It is aligning. That's just, I can say it is just giving a small impulse. Now due to that impulse, all the dipoles arrange themselves in one direction, right? Now this arranged dipoles will be having their own magnetic field, right? See, 1, 2, 3, there are multiple dipoles. Multiple dipoles means multiple amount of magnetic field, and that multiple magnetic field will be greater than the induced field or the one which is inducing, right? So suppose if the external magnetic field is only 10 Tesla, the internal magnetic field due to the dipole arrangement becomes 12 Tesla. That is how. So that means what this material is what is it feeling? It feels magnetized. See, initially all the dipoles were arranged in a random motion, no application of field that time, and due to that the net dipole moment or net magnetic moment was zero. So there was no magnetization in this material. There was no magnetic property at that material. Now when I applied magnetic field, these dipoles arranged themselves in a particular direction or in the direction of the applied magnetic field, so that a induced magnetic field was present in this material. Now this induced magnetic field is greater than the cause producing it, which is the external magnetic field, and this presence of magnetic field inside the material due to the application of external field can be told as or called as magnetization of the material. Right, now here we are going to introduce a term called magnetization vector, or it is indicated as symbol M bar in NCERT, but here I will tell you it as I bar because it is confusing. For magnetic moment also you are using M bar, so let's use it as I bar. In NCERT used to see magnetization vector as M bar, we'll use it I bar here. Right, now what is magnetization vector? As per definition, it is net magnetic moment. See guys, I'm not writing the entire word, please write when I am telling you. It's net magnetic moment per unit volume. Net magnetic moment per unit volume. Right, so or that means net magnetic moment, I will write it as M net moment, right, divided by volume is V, that is your I bar. This is by heart the equation, that is in unit volume. If I consider this material in unit volume, how much is the net magnetic moment present? That is known as magnetization. Initially suppose I applied an external magnetic field which is very low, so the arrangement is strictly very less direction oriented like this, right? That means if I consider a unit area here like this, right, so applied magnetic field is less, so induced magnetic, see this two cancel out, so there are only two guys which are in the same direction, so the magnetic field induced in this volume or net magnetic moment in this volume is less, right? Now the same material, I'm going to increase the applied magnetic field. So now suppose all of them have arranged in a particular indicator, and I'm taking the same area like this. Initially there was only two, now how many are there? Three, right? So here when I increase the applied magnetic field, the number of dipoles aligning in the same direction or in the direction of applied magnetic field is increased, right? So I can say magnetization increase or net magnetic moment per unit volume increase. So that means magnetization increase. This is layman thing here, it is very easy to understand. What is the unit of magnetization then? M net or magnetic moment is current into area, right? So I into ampere, right? Or I can say ampere is the area, and this let's say, sorry guys, so M net is I into A divided by V. I'm writing I is ampere, area is meter squared, volume is meter cube, so the unit is ampere meter raised to -1. That is a unit of magnetization vector or I bar. Clear? Right, now let's move on to the next topic, which is the magnetic intensity. I think it is etched in the textbook itself. Okay. So the second term which you have to learn is magnetic intensity. Right, that is H bar. Now what is magnetic intensity? See, what was magnetization's value? What is I and what is H difference? That is which is very important, because this is magnetization vector, this is magnetic intensity. So it is quite similar, right? The terms looks very similar, but both the meanings are very different, right? Both are proportional to each other, but how it is, I will tell you. See, magnetizing field intensity, which is represented by H, is in a natural or in a simple language. If I am having a material like this, material like this, and lot of dipoles are moving in a random motion. I provided some magnetic field from outside, from external section, right? That external energy or that magnetic field's intensity is known as magnetic intensity, right? The intensity of the magnetic field or external magnetic field which is provided to magnetize this object is known as magnetic intensity. Now, after providing a magnetic field of magnetic intensity h bar, a magnetization occurs per unit volume, that is known as I, or that is magnetization vector. Right? I hope you understood. What is magnetic intensity? Magnetic intensity is the intensity of the magnetic field which is applied to a material so that it gets magnetized with the magnetization vector I. So magnetic intensity is external, magnetization vector is internal. Clear? Now, see what was the initially the random motion was less when the external field was less, and the net magnetic moment was also less. The net magnetic moment inside the object was due to two factors. One is the internal factor, right? Due to the alignment of dipoles, that is a magnetic, I would say magnetic action was increased when the increased field. Now there is a second reason, that is external field. So what was the intensity? This intensity is due to its internal motion. Then there is an external field applied, right? So this external field intensity which caused the magnetization of the material is called magnetic intensity, or it was also called magnetizing field intensity. What? Magnetizing field intensity. I hope you remember or understood. The last portion might be it is a little bit problematic, but I hope you understood the theory of it. A field, when it is applied, this object becomes magnetized due to the arrangement, that is the random motion of the dipole was given a proper direction so that it got an magnetic vector or magnetization vector, that is inside property, right? The second factor was the outside section, right? That is the magnetic intensity, that is intensity of the magnetic field which is given from the external section. So that means I can say one thing. When the external field increased, that is BO, BI also increased, right? Internal magnetic field increased, right? Now I can say that means externals, what is actually increasing? Intensity, right? So when H increases, what increases? Magnetization of this object increases, so I can say I increase. And when H increases, the I also increase, right? So that means I can write here in a small way, that is I is proportional to H. Right? Let's keep it as it is. I is proportional to H. How much the magnetic field increases, that much increase in the magnetic field inside the object. How much increase the magnetic intensity, that much is the magnetization of the object. Clear? Now, the object is now magnetized, right? So there is a net magnetic field inside this object, right? Let's say that is B net. Now that B net magnetic field is actually equal to internal magnetic field, that is due to the arrangement of the dipole, plus the external magnetic field which is given, right? This much is clear. External, I hope you understood, the field which you have provided. Internal is due to the dipoles arrangement. So now I'm going to write here, in place of internal I can write was I, in place of external I'm going to write H. Magnetization, magnetic intensity. So B net is like this. This much clear? Right. Now, right, so actually it is not equal, guys, I'm sorry. You have to write proportional, right? Proportional, because not equal. Of course B will be equal to B, but this is not actually magnetic field, right? This is magnetization, this is magnetic field intensity, so it is not B or magnetic field as it is. So I am writing it as proportional. So in order to remove proportional, I am going to write a constant which is permeability of free space. I hope you remember the value, that is 4 pi into 10 to the power minus 7. That is mu 0 into, I am writing here this in a different order, H plus I, that is B net is equal to mu naught into H plus I. These are all very important equations, okay? Right? I can even rearrange it. That is in problems, some of the problems I can rearrange it like this, B by mu naught, right? minus I is equal to H bar, right? Same. I've just rearranged the equation, right? And I can say, see, I and H are proportional. That means both are having same unit, which is ampere meter raised to minus 1, right? Magnetic field intensity and magnetization both are having same unit. That's why it is having a little bit confusion, guys, right? Now I'm going back to the same equation as the previous one, that is I is proportional to H. Again, this proportional I can remove, right? So here I can write I proportional to H can be written as I vector is equal to, I'm writing a constant, that is zeta, or it is chi into H, right? Removing this proportional, and this zeta is known as magnetic susceptibility. It is magnetic susceptibility, right? How much susceptible this object is towards magnetism, that is given by the term susceptibility, right? And it depends upon the material which you are taking and temperature, etc., right? For different objects there is different susceptibility, right? See how much the field intensity increases, how that much increase the magnetization of the material, and also that depends upon the material where you're giving the magnetic field, right? This much clear, right? Now I'm stopping it, guys, because now after this section a lot of formulas, small formulas are coming up, but I think it is better I stop here. Then we'll go with the revision section, or I will just brush it up. So initially we started with what? Magnetization of matter. We dealt with a single electron, which in the previous class. Here we are going to take the matter as a collection of lot of atoms, and I'm taking an example, helium, and in chemistry would have learned it as a diamagnetic object. Why? Helium is having a pair of two electrons, and each electron is having different spin. So each spin, if I am considering, is causing the electron moment or a magnetic moment, because each electron when revolves it acts as a current carrying coil. Current carrying coil will actually produce a magnetic moment, and each moment of this individual electron are cancelling out each other, so that net dipole moment of helium is 0. Hence I can say almost all the paired electron atoms are diamagnetic materials, or in terms of atomic dipole, there is no atomic dipole in the case of a diamagnetic objects, right? The atoms doesn't have a dipole formation. Net magnetic moment is 0, right, in the case of a diamagnetic object. Now I am similarly going to tell about para as well as ferro. When para or ferro is taken, they are having unpaired electrons, right? So each electron will be moving in a random motion. But if I consider a small unit volume inside that area, inside the material, I can see that these two electrons are having dipole moments in opposite direction. They can negate, right? So since the random motion is happening every time in the case of para and ferro, when no external magnetic field is applied, a ferro and paramagnetic material's net magnetic moment is 0. Right. Now what happens if I give an external magnetic field? This external magnetic field causes the electrons, right, which is moving in a random motion, or in terms of, now we write in place of electrons, I will talk in terms of what? Dipoles. It will say when the external field is applied, all the dipoles which were in random motion will be aligning in a particular direction as that of the applied magnetic field. That is, it is experiencing a torque. So that net dipole, there is a particular direction, so that there is a net magnetic field, right? This is not equal to 0. So external magnetic field is inducing an internal magnetic field, and this internal magnetic field is caused by the what? Particular motion or particular direction motion of the dipoles inside it. Clear? Now applied magnetic field is acting as a trigger only. The internal magnetic field will be usually greater than the applied magnetic field. Now net magnetic moment in a particular volume is termed as magnetization vector, which is I bar here. Right. As the magnetic field increases, that means increase in the magnetization vector. So there is a term which is related with B, that is known as H, that is magnetic field intensity of the applied field. As the magnetic field intensity increases, I bar also increases, right? Clear? That's why I is proportional to H, and note to remove proportion, I am putting a constant chi or zeta, and that is known as susceptibility. As susceptibility increases, that increases how much or shows how much good it is towards magnetization. Clear? Now similarly, I can say the net magnetic field of this entire scenario after applying a magnetic field is equal to the applied magnetic field plus the internal magnetic field inside the material. So internal magnetic field is proportional to the magnetization of it, external magnetic field is proportional to the intensity of it. So I am writing B net is proportional to I plus H. In order to remove this proportional, I am putting a constant, that is permeability of free space, right? You get an equation like this. Clear?